to have the honor to introduce our presenter for today's training, John Nielsen Gammon. John has been on the faculty of Texas A&M University since 1991. He is a Regents Professor of Atmospheric Sciences and also serves as the Texas State Climatologist. He graduated from MIT, receiving a PhD there in 1990. He does research on various types of extreme weather, from droughts to floods, as well as air pollution and computer modeling. As the Texas State Climatologist, he helps the state of Texas make the best possible use of weather and climate information through applied research, outreach, and service on state-level committees. He is a member of the American Meteorological Society. Now I'll call on John to give us his presentation on the future climate-driven drought challenges for Texas. What do we really need to know? John.
Yeah, thank you very much for that introduction and the invitation to present to you today. First off, a couple of preliminaries. It's not just me responsible for this information. This is results of a paper that's was several years in the making and has quite a list of co-authors from people across the state, supported by the National Science Foundation, the Cynthia and George Mitchell Foundation, and University of Texas at Austin. Even though I'm at Texas A&M University, we do occasionally cooperate now that we no longer play each other in football. Other preliminary, before I get to talking about drought, we did have a rather interesting weather event intervene between when this topic was chosen and today, and that was the extreme cold in the middle of February, which I'm sure is on a lot of people's minds. So I just want to take a couple minutes to show the results of some very preliminary analyses I've done to put the event in historical context. In terms of the average minimum temperature on particular days across the state of Texas in the historical record, Monday and Tuesday in week of mid-February in 2021 rank among the 15 coldest. There was one day in 1899, which is quite an impressive event, and in fact, several events from the 1800s shown in blue are among the coldest. The other reference point was 1989, which is the second coldest day, as well as 13th coldest. Temperatures in the 1980s are shown in orange, and gray is all the other events, which actually aren't all that prominent. But the thing about this event wasn't that it got really cold at night, it's that it got cold the whole time. If we look at the average daily temperature and weight the averages so that it focuses on where people live within the state of Texas, this comes out the third coldest day ever on February 15th and the 10th coldest day ever on February 16th, with records going back to about 1881. Another recent event that's been discussed was 2011, which on this scale is doesn't even make the top 15 list. It was about 6 degrees warmer on average across the state of Texas than what we just experienced. And of course, the event was not experienced so much on an average basis by individual locations. Probably the most remarkable time series I was able to find was from Jacksonville, Texas, which is just south of Tyler in East Texas. And this is a standard chart that we use that shows with the blue bars the range between the high temperature for the day and the low temperature for the day in the context of the normal temperatures in orange, and then the all-time record highs and lows in red and blue. And except for a period in the middle of February, it was a fairly normal winter, actually a bit warmer than normal. Actually broke and set a few high temperature records in that period. But then we had a bit different weather experience in the middle of February, where the all-time record low temperature going back to the 1950s was broken by 11 degrees. The all-time record low high temperature for the day was also broken by 11 degrees. And effectively, the bottom dropped out of the temperature record for a few days before promptly recovering again. I could, of course, talk about this event all day, but let's go on to drought and climate change and what sort of information mismatch there is between what scientists are able to provide or typically provide and what actually needs to be known by decision makers. There was, by the way, variety of news stories about the February 15 event in the context of it was an extreme event, so it was probably caused by climate change. Actually, the majority of experts in the field, including myself, think that the evidence strongly points toward climate change making events like this in Texas less likely rather than more likely. And the main driver of that is the fact that temperatures are getting warmer. And so even if we get a blast of cold air from the north, it's going to tend to be warmer than it would have been otherwise. The annual temperatures in Texas have been going up over the long haul over the past century, and most especially since the 1970s. They've been increasing faster than the globe as a whole. The background graphs here are a couple of surface temperature records, as well as an ensemble of climate model simulations, all of which stay pretty well on track with each other. And across Texas, it's fairly uniform warming. Temperatures are going up over the past few decades by about a little more than half a degree Fahrenheit or a third of a degree Celsius, without much geographical variation, maybe a little bit faster to the south than to the north. That's going to impact drought. We'll cycle back on that and see why. But the more obvious effect on drought is going to be from changes in precipitation, if there are changes in precipitation. This is a bar chart which goes to 0, so you can see how variable the annual precipitation is just averaged across the state of Texas. And we've experienced some of that. 2011, one of the driest years ever. 2015, the hottest year ever. And to find any sort of trend, you have to go quite a bit farther back and look at the change over the entire period of record. And there we find there is a substantial trend, especially in central and eastern Texas, of increasing rainfall, about 10 to 20% over the course of the century. Whereas West Texas has been fairly flat, very little change in precipitation over the same period. But the variability, of course, is pretty large, more than a factor of 2 difference between the driest year of the past decade and the wettest year of the past decade. Now, with that background, there have been a lot of studies looking at drought and having some ominous findings for places like the Southwest and the Central Plains. I'm going to highlight a couple of those studies that have come out fairly recently, and then talk about how those don't really give us what we need to know for Texas, and look at some, at least an extension of that for Texas. And then talk about how even that really doesn't get you to the key question of what's going to happen for agriculture and water supplies, and what information we really would need in addition. So this paper made a fairly big splash when it came out in 2015, talking about unprecedented drought risk in the American Southwest and Central Plains. And a key figure from that is showing 3 different measures of dryness. This is using a projection called RCP 8.5, and is coupling it with drought estimates from tree records going back about a millennium or so. Now, all of the projections I show you are going to be, or unless I say otherwise, RCP 8.5, which is sort of a high-end business as usual scenario. So it's close to a worst case scenario. It's most experts don't think that emissions will be that high, even if we don't take additional action on climate change. But looking at this extreme scenario is useful because it improves the signal to noise ratio. We can see what the tendency is that's being driven by climate change. And in that context, um, for both of the regions that were addressed here, Central Plains and Southwest, there's a large decrease of soil moisture and this one particular drought measure that would be unprecedented looking at a decadal scale over the past millennium. Another study followed up on that, looked at what was driving that sort of thing, especially in the context of the southwestern United States writ large. And here again, we're looking at soil moisture, um, and all of the different lines correspond to different model simulations of historical soil moisture, which indicate a fairly gradual drying trend being caused by climate change, but with an awful lot of variability in the individual model runs, mainly due to natural variability being simulated by the models. But around about 2000, the trend becomes fairly substantial and starts emerging from natural variability in the models. So the question is, okay, well, based on tree rings, how unusual is that? And based on the models, what's driving it? For tree rings, um, the top part is showing that as time goes on, we get more and more records that are better and better correlated with soil moisture in the summertime in the southwestern US. So after about, say, 15 or 1600, it's a pretty good reconstruction. But even going farther back, we get some information. And on the bottom, we see in pink and red periods where soil moisture was substantially lower than normal for an extended period of time. And those are called mega droughts. And then the observed record recently has the average over the past 19 years, which is when the current drought started, being comparable to those previous conditions. And if you try to break this down into what's going on with it, the effect of, so the black line in the background is the observations, and which includes, of course, lots of natural variability. Then the gray lines and the colored lines are the individual model simulations and the average of the model simulations. So the average of the model simulation says that precipitation, graphed here in the upper left, its impact is probably fairly small. Different models say it could cause moistening and could cause drying, but pretty small in the context of the trend we've seen. If you factor in the effect of, just consider the effect of temperature and moisture, you see drying, which could potentially account for more than half of the present day soil moisture conditions. Basically, combine the two, the drying trend is contributed by the basically the atmosphere more able to suck moisture out of the ground, whereas the range of possibilities given by the many possible outcomes for precipitation due to both trends and natural variability. So the lesson there is we've got this underlying drying trend in the southwestern United States that's being driven by increased temperatures, but the actual dryness we experience is going to be affected substantially by year to year and decade to decade variations of rainfall. Now, this particular analysis focused on the western US, partly because that's where we have good long-term tree ring records, and only the extreme western corner of Texas got included in this, and presumably what's happening in the western US isn't necessarily representative of that particular corner of Texas, let alone the rest of the Lone Star State. By the same token, that previous study I looked at did include the northern half of Texas, but it also included the southern half of Minnesota. So it's not clear that you'd be able to say that Texas is experiencing the same thing or will experience the same thing as is being projected for the Central Plains, even if those projections turn out to be correct. So for our analysis, we went back and looked at West Texas and East Texas. Broke it up into two pieces, partly because the climates are so different, and also partly because the tree ring records are coming from the western United States for West Texas, and they're coming from the piney woods and the Ozarks mainly for East Texas for the historical perspective. So, not too surprisingly, we see extended periods of drought in West Texas and East Texas as well in the tree ring records. They aren't, interestingly enough, happening generally at exactly the same time. There's not that much overlap. There's some overlap that you can find in recent times, such as the 1950s was dry in West Texas and East Texas. It didn't last long enough to fit the definition of a mega drought, though. The dryness around the Civil War era in the 1800s managed to be pretty dry in both regions, but it was only lasted long enough to be a mega drought really in West Texas. East Texas had relief during the latter part of that period. But we do know from these tree ring data that it probably was dry for long periods in the past as well, of course, for natural causes. Now here's the analogous plot for West Texas and East Texas showing the trends going forward. And the two of them are fairly similar. Let's just focus on East Texas, since that's where the majority of Texans live. Three things being plotted here: model simulations of the Palmer Drought Severity Index, which is a standard index, and then soil moisture average over the top 30 centimeters of soil, and average over the top 2 meters of soil. So you can think of it as shallow moisture and deep soil, or agriculture relevant versus forest relevant and stream flow relevant. I personally don't put a whole lot of weight in the Palmer Drought Index because there's some funny stuff there with respect to how temperature is assumed to affect things. I think it's a bit better to look at soil moisture, which is at least more physically based representation of what's going on. What we see is a downward trend in the topsoil moisture, not too dramatic, but downward. A bit more of a dramatic decline in the deep soil moisture. Now, you notice these are all on the same scale. It's normalized. In fact, it's normalized based on historical record and historical variability. So part of the dramatic decline in 2 meter soil moisture is going to be partly due to the fact that 2 meter soil moisture doesn't have that much variability from year to year. So in a historical context, the decline of soil moisture at 2 meters in these models is more dramatic, whereas it may not actually represent a greater decline of soil moisture in absolute terms. Talking about climate models in aggregate hides a lot of variability based on how different models are trying to simulate things. And this is the correlation among those three different measures of dryness across the full set of models for West Texas and East Texas. And basically the only message here is that some models show a more consistent pattern than others do. The other message I want to leave you with is, if I wanted to talk about a more complicated figure for my paper, I could, but I'm not going to. Instead, I'm going to simplify things with this figure, which is for West Texas and East Texas, showing the variation of projections for these three indices and the range of the model projections. For the topsoil moisture, the range, and this is the interquartile range, goes all the way up to 0, which is to say that 25% of climate models project an increase of moisture in East Texas for topsoil, and almost 25% project an increase in the deep soil moisture, where there's quite a bit more variability in the picture. In West Texas, it's a bit more certain that things are going to become drier overall, which actually is consistent with the trend we've seen in precipitation over the past century. And this is what things look like from a distributional framework. Basically, we're getting more variability in 2 meter soil moisture, but not in the topsoil moisture. The topsoil moisture picture mainly is just a shift in the distribution toward drier conditions overall. And in that sense, we perhaps shouldn't be talking about this in the context of droughts getting worse. Perhaps we should be talking about it in the context of increased aridity. because basically the overall climate system is becoming drier under these projections. Talking about in terms of increased drought may be misleading for decision makers because it implies, well, we're going to have more intense droughts, but they might last for perhaps as long or we'll recover from them. Whereas we're talking about permanently drier conditions whereby if a reservoir was typically able to just barely recover between droughts, it wouldn't be as likely to recover between future droughts. So I've just been showing you model simulations and historical observations, and the historical observations really don't convincingly give us information on a drought trend. The models convincingly, well, the models are saying there'll be a trend in drought, but to really be confident in these models in the absence of an emerged signal in the observations, we want to figure out what's causing the models to be simulating increased drought and take a look at what extent those drivers are plausible or maybe present in the observations already. So I've broken things down into different factors that can affect drought or aridity. Some of them leading to drying, some leading to wetting, and some that it depends. And I'll get to the it depends part in a minute. But first off, obviously, if precipitation decreases, we'll be drier. If precipitation increases, we'd be wetter in that tendency, at least, all other things being equal. And I put this in both columns because it's not clear what the trend in future precipitation is going to be. I noted the historical trend is for increased precipitation. The model trend is for a slight decrease of precipitation going forward. So this one is still in the balance as to how precipitation will be affecting future drought and water supply in terms of the annual average precipitation. I mentioned increases of temperature and associated increased capacity of the atmosphere to drive evapotranspiration would have a drying trend. And I don't have a corresponding decreases of temperature on the other side of this balance sheet because it's pretty darn clear at this point that temperatures over the long term, on a multi-decadal scale, are going to continue increasing. Likewise, there's fairly solid evidence that rainfall extremes are going to increase, and that causes greater short-term droughts because you have longer and more intense dry periods. Changes in rainfall seasonality, right now, both the observed trends and the models indicate that if it is going to become drier, it's going to become drier most strongly in the summertime in terms of precipitation. So winter is becoming wetter, summer is becoming drier is a plausible outcome here, and that would lead to more intense drought overall because it's summertime in which we tend to have the moisture deficits. Lastly, increase in the growth of plants due to carbon dioxide fertilization would lead to drying because plants would be transpiring more water vapor through increased biomass. But that factor is probably overweighed by increased biosphere water use efficiency. What's going on here is just the increase of carbon dioxide itself means that plants don't need to have their stomata open as much in order to take in the carbon dioxide they need to build biomass. So from a water perspective, it means they're losing less water to do what they need to do, so they're using water more efficiently. And that means that they're transpiring less water, so more water would stay within the hydrosphere in the ground or in streams. And right now it looks like the increased water use efficiency is likely to outweigh the increase in biomass on the short term, and even on the long term, maybe biomass wouldn't increase after all as the ecosystems adjust to a drier climate. Mixed effect side. this is where it depends on what exactly you're concerned about with drought. We have meteorological drought, which is a decrease of precipitation or change in a drought index. But drought is important to society because of its impacts. And agricultural impacts and water supply impacts can be in opposite directions for certain types of changes. For example, if we have increases of intensity of rainfall on an individual storm basis, that would change the fraction of water which infiltrates into the soil versus the fraction that runs off. Well, that means that all other things being equal, soils would become drier, but reservoir inflows would become greater. So, a factor leading to worse droughts for agricultural purposes, but less severe droughts for surface water supply purposes. Same thing with all the things affecting soil moisture. If soil moisture decreases, you have a direct effect on agriculture. But in terms of, say, runoff, it sort of depends on, it's a different magnitude of effect, because decreases in soil moisture only matter to the extent that you get the soil saturated before runoff occurs. So there's a bit of a difference in the magnitude of the effect depending on where you're looking there. So let's look at it in terms of surface water supply. And so to say what's going to happen, not only do we have to keep track of all those effects, but there's a whole lot of bigger questions to deal with, such as, we don't know what future carbon dioxide concentration in the atmosphere are going to be. We don't know to what extent the Paris Accords are going to stay in effect, to what extent countries are going to set ambitious targets, to what extent countries are going to meet those targets. So in terms of planning for whatever climate we're going to get, we don't know in what way we're going to be affecting the climate in the first place to any degree of certainty, except on the very short term, when it doesn't really matter so much because natural variability is still large. We don't know exactly how much the climate system is going to respond in terms of like climate sensitivity. We have that to maybe a factor of 2. Factor 2 can make a big difference in consequences. What about the local details? Climate models are simulating things on a fairly broad scale with a fairly crude and coarse representation of the land surface processes, the things that give us our maximum precipitation in late spring and early fall, for example, in Texas. How do we simulate what's going to happen to the hydrologic system, given what the climate system's doing? And how important is all this compared to natural variability? There's a couple, sorts of tools that have been developed to tackle some of those issues. For example, you can combine downscale climate model projections to a hydrologic model with a reservoir, simulating the operating rules for the reservoir. And this is a figure reproduced in our paper, showing basically different versions of the 1950s drought based on different water demand, showing how changes in demand would affect things. And then some scenarios for drought in the 21st century, early and late, showing basically that future droughts would last longer and provide for less storage, given the fact that there's less opportunity to recover between the droughts. Another way of looking at things from some recent papers is breaking down some of these uncertainty factors using, unfortunately, these acronyms for them, but I'll walk you through what they mean. This is looking at the portion of the uncertainty that's coming from different factors. So the contribution uncertainty goes from blue to red, and that's fractional uncertainty. Obviously, the uncertainty in the year 2090 is a whole lot bigger than the uncertainty in the models in the year 2010. But breaking it down a bit, what we emit is actually not a large source of uncertainty here. Natural variability matters in the short term. Eventually, the climate signal, whatever it is going to dominate. But what that climate signal is the biggest question. No matter where you look, really, in the United States, whether it's the global climate models or translating that into the hydrologic models and how the hydrologic system responds. So I summarize that into models are, whatever, in the sense that we really, even if we knew exactly what was going to happen to the climate, to the greenhouse gases, and even if we knew exactly what would happen with respect to natural variability, we still wouldn't have confident projections of how the hydrologic system responds due to the shortcomings in representing things as fundamental as, will rainfall increase or decrease? Or how does this change in intensity of rainfall translate into intensity of runoff? Those sorts of issues. And here's another study that looked at how runoff might change. You're looking at a whole range of models so you can get a sense of the pattern of the projections. Obviously, uniform agreement, temperature is going up. In terms of precipitation change, Texas is right on the dividing line between models where they show, yes, it's definitely going to get wetter in Canada, and it's probably going to get drier in Mexico, but Texas, it's sort of a flip of the coin and may not change at all. Translate those two factors into runoff change. The general projection is for a decrease of runoff, mainly due to a decrease of runoff efficiency, shown here on the right. Let's zoom in on that runoff projection. You can see that it varies a lot from West Texas to East Texas, but the hatching and the dots are various thresholds of confidence within the model range. So even given the strong projected possible signal with the ensemble mean of the models, it's not written in stone, as it were, that we would actually see a decrease in runoff, although it would certainly be prudent to allow for the possibility of a rather substantial change in runoff going forward. And again, this is with the most extreme climate scenario. You can pretty much scale things back proportionally based on what you think is an appropriate climate scenario for planning purposes. Okay, so that's surface water. What about groundwater? Well, it sort of depends on the aquifer, right? If you got a fast recharge aquifer, such as the Edwards aquifer, supply is going to be driving things. How much water is actually making it into the aquifer, and so forth. Whereas for aquifers which are very slow recharge, and here now the name is slipping my mind, the aquifer in West Texas, Ogallala Aquifer, is not recharging hardly at all. So climate change is going to affect that aquifer mainly by how rapidly water is being drawn from the aquifer for primarily irrigation purposes, or perhaps for urban use or for oil and gas extraction. Most aquifers are going to lie somewhere in between those two extremes, which means you've got this complex interplay between climate affecting demand and climate affecting supply. So in the paper, we walk through a few prototypical examples of the different types of information needs for different customers. So I'll summarize those 4 items and then conclude with a description of what one particular water supplier did and to what extent that model could be applied elsewhere. So, first example, agricultural producers. You do, to some extent, want to know about long-term changes in climate, but generally speaking, you're an agricultural producer, you want to know what's going to happen over the next several months. Your decisions are primarily shorter than a year-long time frame. Okay, which crop should I plant? Should I go for a drought-tolerant variety, and so forth? So folks like those are desperate for accurate seasonal forecasts, which are available. Less readily available are prediction of chances of extreme events that might have critical impacts on operations, such as the likelihood that a severe cold snap would wipe out the entire crop of Valencia oranges in the lower Rio Grande Valley. That would have been useful to know if we had the capacity of predicting that sort of thing um, much in advance. Unfortunately, we probably don't. We can just say things about the long-term chances of those sorts of things, which will certainly be very important if producers down there need to replant. It's useful to talk about recent history of weather and climate change context, such as, well, okay, we had this event. What are the odds of this event going forward? That's the sort of thing that's more easy to understand and make decisions on, rather than some abstract event, such as a 100-year event, which never exactly actually happens. There are longer term questions, particularly for orchards, or for planning long term in terms of what sorts of crops would be more suited for future climate compared to current climate, so that you aren't just making decisions based on short term outcomes, but also on long term outcomes. Next example, large surface water supplier. Right now in Texas, water supply planning, it tends to be centered around a repeat of the drought of record. Well, if you're a large water supplier, you know you have to plan for the drought of record, but you might also want to know what sort of inherent risk is built into planning for the drought of record. In other words, is the drought of record now presently something that should be expected to happen with a 1% probability in any given year, or 0.5%, or 2%, or 5%? Those mean very different things as to what sort of safety margin to apply in addition to the drought of record. Another thing that is necessary, that isn't necessarily widely available, is a way to deal with future uncertainties in the context of scenario planning. In other words, we can say, okay, well, it's possible the rainfall will decrease by 15%, and so we can come up with a scenario for that. But if you're using that scenario for planning, you really want to know how much you should take that scenario as a credible outcome versus an extreme outlier case. And we do have an excellent, well-established modeling framework for both surface water and groundwater, for that matter. But they were never designed to be able to incorporate climate model projections, for example, and they really aren't set up with an easy way of incorporating climate change information. And so that's another big need for water suppliers to be able to actually make long-range planning with all information available to them, where the information really isn't very well integrated at this point. Third example, let's go down in scale and go down in the earth as well, to groundwater management district. How the heck are you going to predict what people are going to need for water supply in the future due to climate change? We do that presently for population growth. Is challenging to project, but we're comfortable with that in our planning for future water needs. So we can say, well, more people means more water use. People using water more efficiently would mean less water use. Those two things are working against each other. And then how do higher temperatures lead to things? And that's something beyond really what a climate scientist can provide. For example, to what extent is the recent cold snap going to cause people to plant more native plant species and consequently not need as much urban irrigation resources available to them? Or is it going to go the other way, and people coming back with the same plants as before, and the warmer climate making those plants more suitable to the future climate, but needing more water as well? those sorts of questions. There's also typically, for the small groundwater management district, a limited amount of technical expertise. Um, and I don't mean that in how to operate the system. I mean that in terms of how to actually understand and make use of things like climate projections. Um, and the short-term and long-term outlooks really need to be tailored to the needs of the groundwater management district. There are certain, desired future conditions as well. How would climate change affect the ability to achieve those desired future conditions? You're not going to get a map of Texas that shows the percent likelihood of failing to meet desired future conditions under a particular climate scenario, because those are very location-specific, individualized questions, not just for what those conditions are, but how the aquifer is going to respond to climate change. So way beyond what climate scientists will be able to provide information to get to what a groundwater management district would actually need to know. And the fourth case, regional water planning group. Now we're looking at looking more holistically at a variety of surfaces, variety of customers, variety of uses. So understanding how climate is going to interact with all these sorts of systems is important. Again, we saw an example of system interaction with the cold snap in mid-February. I haven't talked to any water suppliers, but I imagine water suppliers, when planning for cold weather, were more concerned with making sure that their treatment plants and supplies would be resilient to the cold, would not have major lines freezing, not have equipment freezing, and so forth, and may not have been recognizing the probability of rolling blackouts and long-term blackouts accompanying the cold weather. That's an example where you have the knock-on effects, a cascade of impacts. For future aridity, rising temperatures leading to rising energy demand, which may lead to increased needs for cooling water at the same time that the ambient water temperatures within lakes is higher because of climate change. So those sorts of interactions need to be dealt with, and even identifying those interactions is a challenge. Also necessary tools for figuring out how you make a water supply that's climate resilient. I spent a lot of time in this presentation talking about all the uncertainties. Well, you still need to go forward with planning in the face of uncertainties. And the answer there is often have a supply that can deal with a realistic range of possibilities. So how do you design that sort of thing? How do you actually deal with a reasonable range of scenarios that involves different things happening simultaneously? Is the high end of temperature projections consistent with precipitation increasing? Is that a possible scenario, or does a large temperature increase imply decreased precipitation? Those sorts of interactions need to be dealt with to make an intelligent plan. And in all of that, you've got to deal with the diverse stakeholders and diverse public opinions about to what extent any of those projections ought to be treated as being credible. As a climate scientist, I can make an expert judgment as to what would be credible and what's not. But ultimately, regional water planning groups are composed of stakeholders, and they don't answer to climate scientists. They answer to themselves and to their constituents. And so whatever plan is put in place needs to be done in a way that makes sense to the people who are going to be impacted by the plan. So here's an example, Austin Water. They did a forward-looking water plan looking 100 years into the future. And they dealt with some of the shortcomings of the availability of knowledge by sort of compartmentalizing things. But they had the resources to be able to do those sorts of compartmentalized studies in a way that were specifically germane to the questions that they needed answered. So, for example, they obtained, through sponsored research, global climate model projections specific to stream flow gauges within their water supply catchment areas. They had someone develop the regression equations to relate changes in temperature and rainfall to changes in stream flow based on historical data. They decided to go with future scenarios that included basically the drought of record and a scenario that would be 3 times as severe as that in terms of impact on water supplies. And they went through this framework in part because all of the stuff they were generating could be plugged directly into the water availability model and be used then for the rest of the planning purposes. In terms of the success of this effort, well, we won't know how successful planning is for another 100 years, but the perceived success of the process relied in part on working directly with climate scientists because that meant that the climate scientists were providing information that that was going to be useful because they were supplying what the stated needs for information were. And furthermore, the stakeholders were able to interact with the climate scientists and understanding what sort of information climate scientists could provide and how much credibility to attach to that sort of information. And that's the sort of thing that you can do if you're a major city water supplier, but not every stakeholder in this realm is going to be able to do that sort of thing. So what sort of things can be done going forward that would benefit stakeholders and improve the integration of scientific and information with planning needs? Well, understanding what natural variability can do over a longer term would be useful because even for stakeholders that don't buy into what scientists are saying about climate change, they would still be generally willing to accept what has happened historically in terms of how bad drought can get. Developing tools to connect, whoops, a little typo there, let me fix that. Downscale projections and local stream flow in a more seamless manner rather than the projection, downscaling, regression, then LAM as a sequence of events. It'd be great to be able to have a tool where you could actually use whatever projections and scenarios you wanted and have that be seamlessly integrated into surface water and groundwater models. To what extent should the drought of record be adjusted to ensure future resilience, assuming we still use some sort of concrete historic drought? Being able to tweak that and say, okay, well, what would that drought look like in a future climate? Or be able to say, okay, our resilience is decreasing because this sort of drought would be changing in frequency by such and such amount. Some way of at least nudging water planning in a way that can deal with climate change without doing a wholesale revision of how it's done, because there are a lot of reasons for preserving the current sort of framework. And lastly, this is on climate scientists, transparent communication and helping people understand what the unknowns are with climate change, why many of these gaps are gaps which aren't going to be reduced anytime soon. And, unfortunately, we have to do our planning in the face of this uncertainty. And sometimes it's uncomfortable, but unfortunately, that's what we're stuck with. Okay, so most of what I've talked about is in our paper, which you can find. It's open access. You can Google my name and the journal name, which is Earth's Future. Somewhat pretentious, but hey, that's life. And if you have questions that I don't have time to answer before the end of this webinar, you can email me. My email address is up there on the screen, n-g@taamu.edu. So with that, I'll stop and be happy to take questions.
All right, thank you, John. Are there some questions? We appreciate the presentation. It's very informative and raises some very interesting things in terms of existing codes. Have you seen any changes in any of the codes that relate to temperature for engineering design or rainfall for engineering design?
I haven't seen any changes yet. There was legislation introduced at the federal level last week that would try to bring rainfall frequency analysis into a climate change context. It would start with the National Academy's report being commissioned on that, which I think is a good way to go, because some of the ways of dealing with that is, needs to get to something that would be acceptable from an engineering framework before it can really be utilized. I've done some work in that space for the Harris County Flecktonville District, and by the way, I'll be talking to that section, the Southeast Texas or Houston section of ASC next week on the results of that report. In terms of, and I'll also notice that the legislation being filed in response to this event for resilience of electrical supplies is taking different approaches for this sort of thing. One is basically saying it needs to be resilient and basically leaving it up to regulators to decide what that is. Others are saying, okay, it needs to be resilient to the event in 2021 and 2011 and 1989. Others are saying it needs to be resilient to temperature of 0 degrees Fahrenheit for 2 days or something like that. Another one mentioned -40, which I suppose works whether in Celsius or Fahrenheit, but that's the only reason I could think of you putting -40 into the legislation.
We have a question from Mark. What is your opinion of the new Atlas 14?
Well, let's see. For what it is, it's great. For the Harris County study, what we focused on were two big questions they had. One was, how much are the Atlas 14 numbers reliable, given that Houston have had lots of bad rainfall events recently? Does that skew the numbers upward in Atlas 14? Are they going to be, over resilient, so to speak? And the other question was, well, what about climate change? Are we going to be under resilient? So I focused on both of those issues in my evaluation. And by the way, I should say I was part of the external review committee while Atlas 14 was being developed for Texas. So I had my say in making sure things at least were consistent with what I wanted to see in that. But of course, it doesn't include those two factors I mentioned. So I looked at that, and as expected, they had competing influences in Southeast Texas, such that for like a 100-year event, they're probably over resilient now, overestimating the odds of heavy rainfall, but climate change will catch up in a few decades. So it's probably not a bad thing. Whereas other parts of the state, the opposite side of the coin, they haven't had the same bad luck that Houston's had. So they're probably already behind the curve in terms of the actual odds of heavy rainfall being higher than what NOAA Atlas 14 produces, because Atlas 14 is a historical analysis. It says what the odds were. It doesn't say what the odds are now or what they're going to be, even though they get used for that purpose.
And John had a compliment, enjoyed your discussion, and he asked if your research has been shared with the Texas Water Development Board.
Well, it's certainly out there. I haven't been asked to give a in-house briefing to them, but I'm sure they're aware of all of this. We did do a series of op-eds around various newspapers around the state to make sure that this was information was available to decision makers and to the general public. But they have not had a dialogue with me on any of the implications of this. And they, when Robert Mace was on the Water Development Board, he argued that you really need to have something like the drought of record as a planning target, because you can calibrate your models and you can do everything to that. And I understand that position, and I'm not in a position to argue that that's not the appropriate framework.
And one final question from Zai Hong. He says, does it mean for summer the drought is worse and more snow and rain during the winter in the future because of climate change?
That's mostly if I were going to bet on the most likely outcome, I would say drier in the summer. I wouldn't be too confident about more rain in the winter. Maybe the odds are slightly better than 50%, but not a whole lot. Snowfall actually would decrease in magnitude and likelihood because of that temperature thing again. Where mainly the question for snow is it going to be cold enough to snow? And it won't be cold enough to snow more often in the future.
All right. Well, thank you very much, Dr. John. We really appreciate your presentation.